Okay, let's do the second problem for today. And the second problem for today is going to be a sort of engine, weird engine here, the way the problem is set up. Engines, we know, create power. That's its whole purpose here. So there's going to be some power, W dot, the control volume. And we're going to bring in three flows here, 1, 2, and 3, and there's going to be water, so it's a water-powered engine or turbine or something that's really happening here. A water engine. We could have some flowing, some paddles or something inside there. But if you can get an engine that runs on water, you know, that's what you should do. You know, during the plague, Newton, I think it was the plague, bubonic plague. I'm not sure about this. Look it up. It's probably I should make it an alternative assignment. Newton came up with all this wonderful stuff during the plague. Maybe you can, solve the world's problems with thermodynamics. That would be worth. If you could solve the world's problems with thermodynamics, that would be worthy of some extra credit for the class. Turn it in. I'll consider it. So let's look at this. This engine here, and we have water here, H2O, and let's look at state 1, state 2, and state 3. In state 1, they tell us the temperature at state 1 is going to be 120 degrees Celsius, and the pressure at state 1 is going to be 5 bar. Okay, state 2, temperature 2 is going to be 240 degrees Celsius, and the pressure 2 is going to be equal to 5 bar. And pressure 3, they're just telling me, is equal to 5 bar. Okay? Now, we know some other things. We know that the mass flow rate at 2 is the 3 times the mass flow rate at 1. And we know the mass flow rate at 3 is equal to 4 kilograms per second. Okay, that's what we know. All right, so here's what we're going to assume in this problem. We are going to assume that this is going to be an adiabatic process. In fact, the problem statement told us this, and I'm not showing you the problem statement directly, but the problem statement said an adiabatic engine. So we're going to look here and say it's adiabatic. We're going to assume the kinetic energy and the potential energy is negligible. Okay. We're going to assume steady state operation. And what I want to find out here is the maximum, or let me say find. I want to find the maximum work. Okay. Maximum work. Maximum work is going to be when sigma is equal to 0, when I can get that reversible situation going on. So that's what I want to find in the situation. So if I'm trying to find the maximum work, I have two laws that I can really deal with, the first law and the second law, and the only one that has work in it is the first law. So I'm going to go here and I'm going to say the change in energy of the control volume with respect to time is equal to Q dot minus W dot plus the summation of my mass flow rates N times my enthalpy N plus my kinetic energy N plus my potential energy N minus the summation of my mass flow rate Xting times the enthalpy Xting, the kinetic energy Xting, and the potential energy Xting. You might have said, Dwayne, why are you doing all that stuff? Because you know it's steady state, you know it's adiabatic, you know there's no kinetic or potential energy effects. All of those things go away. And we're left with, if I move this work to the other side of the equation, of the power, W dot of the control volume is going to be equal to the mass flow rates in, and we have, I made a mistake here. This is a mass flow rate out. I can't have, what I had a situation was it wasn't steady state. You're probably screaming at me, Dr. Winkler, it's not steady state. You can't have all this stuff mass going in and no mass coming out. That's a big mess. Yeah, it is a big mess here. So this mass 3 is going out. Sorry for the trouble that I've caused you, the angst that you've had there in your mind for the last 5 minutes. But our two mass flow rates coming in are going to be mass flow rate 1. It's going to bring in enthalpy 1. Also going to be mass flow rate 2 times the enthalpy 2. And coming out is going to be the mass flow rate of 3 times the enthalpy of 3. That's what we have going on there. Okay, now, I don't know, I mean, we know mass flow rate of 3. We know this. It's this. Mass flow rate of 3 is 4 kilograms per second. Mass 2 is 3 times mass flow rate 1. I don't know what mass flow rate 1 is, but you could probably do this in your head, but if not, we can use our mass continuity equation. Okay, you know, at steady state, we're going to have that 0 is equal to mass flow rate 1, plus 3 times mass flow rate 1 minus 4 kilograms per second. The only way this equation works is if mass flow rate 1 is 1 kilograms per second. Okay, that's pretty straightforward there in that analysis. We could do it up here, or we could write it down. So I know these 3 mass flow rates. Okay, so now my equation is going to be that the power of the control volume is going to be equal to 1 kilogram per second times H1 plus 3 kilograms per second times H2 minus 4 kilograms per second times H3. Okay, now if I go up here, I can set state 1. I have 2 things I can set state 1. I can set state 2. I have 2 things I can set state 2. I do not have enough things to set state 3. I don't have things to set state 3. So in this equation here, I now have H1, I have H2, I have 2 unknowns. Okay? If I have 2 unknowns, I have to use another equation to help find that information. And I know, because of the way the problem statement said, I know where I have to go, and that's going to be the second law of thermodynamics, because I have this other piece of information I have to use, and that is that it's a reversible process. It's a reversible process. Okay? So, the second law, the change in entropy of the control volume with respect to time is equal to Q dot, the summation of the heat transfer rate over the temperature at which that heat transfer rate occurs, plus the summation of the mass flow rates in times the entropy in, minus the summation of the mass flow rates exiting times the entropy exiting, plus sigma dot. Okay? I know it's steady state. I know it's adiabatic. And in this case, I know it's reversible. That's what I'm trying to find out. The reversible situation, the maximum work. So here's where students have to keep thinking about this. To find the maximum work, I'm going to have to use an equation that doesn't have work in it to find a value that I will plug in to the first law. That thinking is what you have to be comfortable with when you work with these kind of problems. Okay, so 0 here is going to equal mass flow rate 1 times entropy 1 plus mass flow rate 2 times entropy 2 minus mass flow rate 3 times entropy 3. Okay, and again, we can set this one and this one and this one and this one, and we know this. Now we have one unknown here, which is S3. And so we will find what entropy 3 is. That will be the second piece of information here if we find entropy 3. If we find that, now we have 2 pieces of information, and now we can set the enthalpy of 3 and go back here and solve our work equation, our power equation. Okay, so if I was in class right now, I would say stop, and I would ask you to pull out your tables, and we would start to set states. So that's what I'm asking you to do here. State 1. Okay, pause if you'd like to. Come back to me, and let's see if we can figure this out. Or if you're on like somebody else, you're eating Oreos and watching me do this, and you don't care. You just want to watch me until I ask you to do a top hat question. State 1, we're going to table A3, and we're going to say, well, at 5 bars, it saturates. Saturation temperature is equal to 151 degrees Celsius. Okay, so we look at this, and we know we saturate at 151. Well, we're at 120. We are a liquid. We're a saturated liquid, a subcooled liquid. So we're going to have to use, I said saturated liquid, I want to say subcooled liquid, a compressed liquid. So we're going to have to use the liquid approximation here. Liquid approximation. So I'm going to say that the enthalpy of 1 is equal to the enthalpy of saturated liquid, and it's important that I do, it's at the temperature, 120 degrees Celsius. I do not look it up at the pressure. I just don't do it. It would be a terrible thing to do. Terrible thing to do. Enthalpy 1 is equal to the enthalpy of the saturated liquid at 120 degrees Celsius. Okay, those two values are 503.71 kilojoules per kilogram and 1.5276 kilojoules per kilogram Kelvin. Okay. State 2. State 2 clearly is going to be, if we look it up, 240 degrees at 5 bars. Well, 240 is up here. We're going to be a superheated vapor. Superheated vapor, and so we're going to go to our superheated vapor tables and find that H2 is going to be equal to 2939.9 kilojoules per kilogram, and we're going to find our entropy is going to be equal to 7.2307 kilojoules per kilogram Kelvin. Okay, straight lookups, no interpolation, none of that. All right. State 3. State 3 is what we're going to try to figure out, and so we're going to now put these two values into the second law. Okay, and so we're going to have here 0 is equal to 1 kilogram per second times 1.5276 kilojoules per kilogram Kelvin plus 3 kilograms per second times 7.2307 kilojoules per kilogram Kelvin plus 4 kilograms per second times S3. We can plug that into our calculators, and we're going to get that S3 is equal to 5.8049 kilojoules per kilogram Kelvin. Okay. And now we're looking at a pressure 3 that's equal to 5 bars. 5 bars. Okay, now if we go to 5 bars and we go to 5, look, and we try to figure out, is this a liquid, is this a vapor, is it a liquid vapor mixture? What we're trying to figure out is it between SF and SG first. That's what we first want to figure out. Is S3 between those two numbers? And the answer that we have is yes, it is, because SG at 5 bars is 6.8212 and SF is equal to 1.8607, and we're someplace in here. Okay, we're a quality that we're looking, it's probably going to be between 70 and 85%. I'm just guessing right now. And so we use the quality equation. S3 is equal to SF plus X times SG minus SF. Okay? 5.8049 is equal to 1.8607 plus X times 6.8212 minus 1.8607. That gives me a quality, when I calculate that, of 0.7951. Now the quality that I find with my entropy is the same quality that would be for my enthalpy. And so I'm going to use that quality to find out what H3 is. H3 is equal to HF plus X times HFG. Okay, this X, this quality is the quality that I use. And so that's going to be the top hat question for you, is going to be to find this H3 and to use the other H's, H1 and H2 that I found in this problem. Go way up here to this equation, and now you can find H3, plug it in there, tell me what the power is in kilowatts. So give me the power. So the top hat question, top hat, is going to be the power in kilowatts. Okay, you're all capable of doing that. I think you're enjoying this. You're ready to go. So enjoy and work on that, and we'll come back. We'll do one more problem here to end today's lecture.